I got no rules, I count 'em. I got no rules, I count 'em. I got no Hi guys, and welcome to today's lesson all about indices and reciprocals. In this topic, we're going to be examining some keywords, and those words are indices, an index, the power, the square root, the product, the standard form, the order of magnitude, and finally, what a reciprocal means. Before we start anything, we need to understand the idea behind powers, and we need to understand the idea about square roots. So the first example we're going to look at is the idea of 3 squared. So what does that mean? Well, if we have a look here, we're looking to the power in this example. Our power is to 2. So all this sentence means is 3 multiplied by itself, which we know to be 9. Let's take another example. Let's look at 5. 5 squared is going to be the exact same. 5 multiplied by 5 is going to leave me with 25. If we have a look at the opposite of this, the square root sign. The square root of 25. What am I asking you here? Well, the square root, I am looking for a number that when you multiply it by itself gives you that number. And in the previous example, you just told me that 5 squared happened to equal 25. And we know that 5 squared is actually equal to 5 multiplied by 5. A number multiplied by itself to give you another number. So this answer, our square root of 25 is 5. That leads me very, very nicely to rule number 1, or law 1 of indices. That says when you have 2 numbers that are the same, but to different powers. So in our case, the powers are P and Q. And when you are multiplying these 2 numbers, if the bottom number is the same, we can add our powers. So in this example, our A's are the same. They are the same letter, and so we can apply this law to them. Our powers are different, and that's okay. But when we multiply, and that's very important, it's that process we're doing, we can add the powers. Let's look at an example. Okay, so the first example that we're going to look at is the idea of 6 to the power of 2 multiplied by 6 to the power of 3. So in this example, my base numbers are both the same, so it means I can apply my law to them. So 6 gets carried over, and this time I can add 2 and 3 together, so my answer ends up being 6 to the power of 5. We can apply the exact same logic to minus numbers. So if I look at minus 7 to the power of 3 multiplied by minus 7 to the power of 4. In this example, my bottom number is the same, so my law 1 applies. However, it's very important to notice the presence of the minus sign. We know that a minus multiplied by a minus gives me a plus. So my answer is actually going to be plus 7 to the power of 7. Law 2 is for the other mathematical principle that we deal with on a daily basis, and that's division. In the same idea as law 1, the base number of both needs to be the same, and the powers again can be different. But in this example, my base numbers are both A. A is just representing an unknown number. And if A stays the same, we can take away our powers. And it's a nice handy trick that we can have to make doing some mathematical equations a little bit easier. Let's have a look. So if we start with an example that reads 7 all to the power of 12 divided by 7 all to the power of 5. Our base numbers in this example are the exact same. My powers are different, but again, that's okay. It's our base numbers that are important. So we know from law 2, I carry down my base number and I take away my 2 powers. So I'm left with 7 to the power of 7. Again, we can do the exact same for negative numbers. So if we have a look, and if we have 2 to the power of 4, but this time we're dividing it by minus 2, all to the power of 2. Now, our numbers are the same, even though our signs in front of them are different. So I can carry my 2 down, but we have to be careful. Side note, revision from last year, a positive sign divided by a negative sign will always give me a negative sign. Different signs means a negative answer. So in this particular example, we have 4 minus 2, so I end up with an answer of 2 all to the power of 2. In Law 3, we're talking about a product of 2 powers. So if I have a base A, and that's to a power P, but now I'm introducing brackets, and that power P is actually all to the power of Q. I have a very nice thing, which means I have base A, and I multiply P by Q. Now notice in this one, I only have one base, but I again have 2 powers, and I also have some brackets. So when I have a base number to the power of one number, all to the power of another, I can multiply the 2 powers, provided my base stays the same. Let's have a look at some examples. So if we have a look at 3 to the power of 6, all to the power of 4. My base number is the same. I have 2 powers, so it ends up being 3 all to the power of 6 multiplied by 4. So I get an answer of 3 to the power of 24. Similarly, with 2 to the power of 4, all to the power of 8, I get a nice answer where 2 stays the same, 4 gets multiplied by 8, and I get 2 to the power of 32. Let's see what happens if we have some negative numbers. So if I had minus 5 all to the power of 3, all to the power of 7. Let's see what happens. Okay? Well, we actually forget about the minus sign and we take that out of the brackets and we treat it just with the 2 powers. And then it becomes like any other sum. Minus 5 all to the power of 3 multiplied by 7, which gives me minus 5 all to the power of 21. The next thing that we need to talk about is writing numbers in scientific notation. And up here you'll see I have a definition outlined. A number is in scientific notation if it is of the form a multiplied by 10 to the power of n, where a must be between 1 and 10 and n is equal to 0, or it's an element of the natural numbers. Let's put this into context. Let's have a look at the number 673. Now, that particular number is just another number. It doesn't seem too big. But if I want to write that in scientific notation, well, 673 is way bigger than 10. Let's see if I move the decimal points. 67. That's still way bigger. Let's move it once more, and now I'm at 6. And we know 6 is under 10. So my answer is now going to read 6.73. Now, I have to take into account that I've moved my decimal point, and that's where the by 10 comes in. So we write down by 10, and how many times do we move the decimal point? Once, twice, so my 10 becomes to the power of 2. Let's apply it to a bigger number. Let's have a look at 980,000. Okay, this number is way bigger than 10, so we have to round it down. And we have to move our decimal point once, twice, 3 times, 4 times, 5 times before my number ends up being under 10. So I get an answer of 9.8 multiplied by 10 all to the power of 5, because I moved my decimal point 5 times. The last definition that we have to talk about is the word reciprocal. When I talk about the word reciprocal, it may be easier to lead with an example. Let's have a look at 2 multiplied by a half. That gives me 1. Let's have a look at 3 multiplied by a third. That also gives me 1. When we multiply two numbers, and if the answer is 1, we say those two numbers are reciprocals of each other. So in this case, 2.5 are reciprocals of each other, and 3 and 1/3 are reciprocals of each other. The product always has to give you the number 1. I'm going to leave you with an example of some minus answers now. -6 all over the 7 multiplied by 7 all over 6. Now in these examples we have to be careful. Minus by a minus gives me a plus, and when I multiply both of these answers I get a 1. But if I was to multiply -6 over 7 by plain old 7 over 6, note that I actually get -1, and this is not a reciprocal pair. In order for it to be a reciprocal pair, we have to end up with a +1. So I hope you enjoyed today's video. And don't forget about those. Until next time.